We're now going to investigate how to create an equation of a line in space in a three-dimensional coordinate system. And we're going to start this off by revisiting what we used to do with lines in 2 dimensions and how we created the equation of that. And we're going to extend that into 3 dimensions. Only now, in order to do the process, we're going to need to use vectors. All right, so let's take a look in 2 dimensions at our line right here on the left. So obviously here's our y-axis and our x-axis. You may remember that in order to find the equation of a line, we needed to know 2 things. We needed to know, first of all, some particular point that was on the line. Let's call it x0, y0. So you definitely needed to know some point that was on the line, but you also needed to know the slope of the line. The slope, which we referred to as m. Because now what that showed is that we were able to find an equation of this line, and I won't go through the proof of this, but it was really just the Pythagorean theorem, where y minus y0 is equal to m times x minus x0. So we're saying that as we move in the y direction, that we could find the corresponding location by just taking the change of y over the change in x and multiplying it by that change in x. So this right here is the equation for a line, point-slope form of a line in 2 dimensions. Now we're going to see that this is somewhat analogous to what we eventually get for the equation of our line in 3 dimensions, and we're going to need to know something similar as well. One thing that we're going to need to know is a point that lies on the line. Only now, that point would be some 3-dimensional point, so x0, y0, z0. Let's just call that right there. Now, there is a vector that extends to that point from the origin, and we often refer to that vector as a position vector. It's demonstrating the position of some point in space. So we're going to refer to that as R0. R from now on is going to be describing the position of some object. Okay. Now it would be helpful as well, just like we did over here, if we ended up having a second point somewhere on the line over here, remember that that would be some point, say, x and y. And I'm not putting subscripts on it because now it could vary, which is where the x and y in our equations ended up coming from. Okay? Well, we could do the same thing over here. Let's just pick some other random point over on the line, but that point can vary. It could be at all kinds of different locations, anywhere. It could be backwards. It could be anywhere. So we're just going to pick some particular point, and we're going to call that point x, y, and z. Okay. All right. Well, what we could do in this particular case is see what the difference between x and x0 is, y and y0, and z0. The problem with this is that we don't have a slope of this line, because there is no such thing as a slope of a line in multiple dimensions. When we're looking at a slope in 2 dimensions, you could say, well, how much does it rise in the y direction compared to how much does it run in the x direction? But if you were to find a slope in 3 dimensions, now I'd have to see how does x change as y changes, how does x change as z changes, how does y change as z changes. There's a lot of different components that come into it. So what we're going to do instead is we're going to look at this in terms of a vector that's parallel to the line. Well, let's start off by demonstrating that this is also going to form a vector. If I extend this all the way, let's see if I could do that with a line. Close. Let's see if we can move it. Okay, we've got another position vector of this other random point on the line, which we're just going to refer to as R. Now I should realize that there are a lot of vectors that are parallel to this line. And so let's just pick one random vector that's parallel to this line, and let's call it vector v. Now in order to find the equation of a line, we would have to end up having some vector that's parallel to it. So we could see that r is doing nothing more than just referring to a vector that's going to extend to the line at different points, depending on where we're at. Okay, well, why don't we go ahead and put this vector on the line, since we can pick it up and move it anywhere we'd like, and that's also vector v. And so now I think that we've got enough to recognize what's actually going to happen here in order to create an equation of a line. Okay, so if I were to refer to this line, let's call this line L. L is going to be the set of all the points called x, y, z, where the line segment from P0, let's label maybe these as point P0, and let's call this point out here point P. Okay, it's a set of all points where P0P is going to be parallel to vector v. Think about that a minute. If I draw a line from P0 to P, a vector from P0 to P, that would be parallel to the vector v. So I know that L is the set of all points where P0P is parallel, or in other words, a scalar multiple of vector v. So what does that mean? What it really means is that P0P will be equal to some scalar multiple of vector v, where t is that scalar multiple. Okay, well, we're getting somewhere, I suppose, now. Let's just say that we have vector v, and vector v is our standard v1, v2, v3. That means that we should be able to come up with an equation for this vector. And so we know that P0P is nothing more than x minus x0 in the I direction, plus y minus y0 in the j direction, plus z minus z0 in the k direction. That's the vector from P0 to P. But notice that that's going to be equal to a scalar multiple of vector v, which is v1i plus v2j plus v3k. And this is assuming that we're given a vector that is parallel to the line. Okay? Well, what you should recognize now is that there's an I component on the left and there's an I component on the right. And there's a j component on the left and a j component on the right, and a k component on the left and a k component on the right. So in general, what we could really do here is manipulate this in a particular way to where I'm going to expand this and move a few things around. I'm going to separate this into xi minus x0i. And so when I have xi minus x0i, and then I have yj, and I have zk, why don't I combine those all together to create a particular vector? Let's look back to what that vector is. That's the vector that ends at xyz. That's called vector r. All right, so that vector that we just created is going to be considered vector r. While we're at it, we're going to move the x0, y0, and z0 over to the other side. by adding each of those terms, okay? So that would mean that we end up getting equals x0i plus y0k, or j, plus z0k. That's the vector that ends at x0, y0, z0. Well, look at that. That's just our r0. So that was our initial point. So we could see that r is going to be the initial point, which we refer to as r0, plus what remains, plus t times vector v. v1i plus v2j plus v3k. So to round out this equation, this right here is the equation, or the vector equation, for a line. So what it's saying is take some vector that we know is parallel to the line and multiply by some scalar, unknown scalar called t. Add to it the initial point, and that will give me a new vector called vector r, or the position vector, that demonstrates every position on that line. But before we continue, I'd like you to see how this kind of looks like y equals mx plus b. This looks very similar to the equation for a line in 2 dimensions, where b is basically the starting point, the y-intercept. M is the amount that we're moving in a certain direction, or the ratio of how we're moving, and x is the distance we're moving, while m is telling us the direction we're moving in, or the slope. But this actually isn't the easiest or best form of the line, even though this is definitely acceptable to write it in this form. It turns out that it's actually easier for us to write this line as a set of parametric equations. So instead, we can actually rewrite that line L as a set of parametric equations. And this is the more standard way to write a line. Okay, the way that we write that is L equals, or rather not L equals, I suppose, just L. And what we're going to do is we're going to determine how can we find X, Y, and Z separately. So let's go back to our picture and think about what we're actually referring to here. On this diagram, what we're trying to do is say, how could we come up with an equation to find every point called x, y, z that lies on a particular line? Well, you definitely need to know the starting point, and you definitely need to know the direction we're moving in. Just like in 2 dimensions, you needed to know the starting point and the direction we're moving in. Well, looking back to this example here, let's just clump together all of the i's and realize that xi on the left side should be equal to x0i plus t times v1i. And then let's look at the j's separately. yj should be the same on the right side as y0j plus t times v2j. In other words, all we're doing for our parametric equations is separating them into their individual components. So x is the initial x value plus t times the x component of the v value. Y is equal to the initial y value plus t times the y component of the direction. And z is equal to z0 plus t times the z component of our direction. And this is the standard way that we're going to be describing lines in space as a set of parametric equations. Looking at this example on how to create the parametric equations for a line through a couple of given points, we need to think about what we need in order to create that equation. So in order to create the equation of a line, we're obviously going to need to know an initial point on the line. Now we have two. It could be either P or Q. It doesn't matter which one we use. But what's more important here is that we need to know a vector that points in the direction of that line. Problem is we weren't given a vector. But what we can do is recognize that if you're given 2 points, you could find a vector that is parallel to that line, because we just have to find the vector PQ. So how about let's make that our V. So our V is the vector PQ, which is going to be 1 minus negative 3, or 4i. Then negative 1 minus 2 is negative 3j. Then 4 minus negative 3 is 7k. So since we now have our initial, or I'm sorry, a direction, and we also have an initial point, whether I call this the initial point, or really I could use Q if I choose to as well. All I need is any point that I know lies on the line. So therefore our line is nothing more than a set of parametric equations where x is equal, y is equal, and z is equal. Well, I know that all I'm going to need is the initial x, y, and z values. So let's use negative 3, 2, and negative 3 for our x, y, and z separately. Plus t times the v components, which is the direction. So t times 4 gives me 4t. T times negative 3 gives me negative 3t. And finally, 7 times t gives me 7t. Or if I chose to, I could have come up with another set of parametric equations by using point Q. The only difference here is that now the initial point has changed, 1, negative 1, and 4. But the direction can't change, right? It's still going to be the same direction regardless of what 2 points I use on the line. And so I simply have to add 4 and t, subtract 3t, and add 7t. So just to demonstrate what the t value means, you can sometimes think of that as time. So let's think of this as a t value of 0. So when t is equal to 0, notice that I get the point negative 3, 2, and negative 3, which means that at point P, I'm at t equals 0. As t gets bigger or smaller, what about when t is equal to, let's say, 1? If t is equal to 1, I can now plug in 1 for all of my t values. And if I do so, I get the point 1, negative 1, and 4. But look at what's cool. That's my point Q. So that's pretty interesting, because what that means is by the time I got to Q, that was when t was equal to 1. But what about when t is equal to negative 1? If t is equal to negative 1, now I end up getting something different. I get a point negative 7, and 5, and negative 10, which would be some other random point on the line back in the other direction when t is equal to negative 1. And I could go all the way out to t equals infinity, getting an infinite number of points that are lying on this line. So that's why this parameterization of the line in 3 dimensions is so beneficial for us, because it allows us to find basically the set of any points given a value of t between negative infinity and infinity. I'd like to make one other note as well, to revisit this form of a line, okay? We learned a couple sections back that you could actually rewrite a vector v as the product of the magnitude times the direction, which should make sense because the magnitudes cancel. But we don't want to cancel them necessarily if what we're looking at here is the speed and the direction. So what we should notice is that this formula is telling me that the position, which is r, is equal to the initial position, which is where we begin, plus some change, plus the time, times the magnitude, which is the speed, times the direction, because v over the magnitude is the direction. But I'd like you to really recognize what's happening as well. If I look at speed times time, or rate times time, that's nothing more than a distance. So essentially what we're saying is in 3 dimensions, we're going to find a position in a very similar way. We're going to say, let's start somewhere and let's add some distance in a certain direction. And that will tell me the position of where I am. So sometimes if what I am given is our speed and our direction and so on, then I don't really want to use the parameterization of a line. Instead, I might want to think about the line in this format here. So let's think about what we're given. In this case, it says that a helicopter flies from a helipad at the origin in the direction of the point 111. And it also tells me the speed is 60 feet per second. So why don't we go ahead and just start listing out the things that we know. All right, so one thing that we know is the speed. All right. I also know that the helicopter is moving from 00 to 11. So why don't we come up with a vector that defines what the helipad is, or where the helicopter is flying. So the helicopter is flying in the direction of 1i plus 1j plus 1k because it left from the origin. Well, that also implies that the magnitude of h is equal to the square root of 1 squared plus 1 squared plus 1 squared, which is root 3. Well, what does that tell us? It tells us the direction it's going in is 111, but that's not quite the direction because the direction is the unit vector. So all we have right here is the speed. We don't quite have the direction yet, but we have its speed. In order to find the direction, we just have to take it a step further and take h over its magnitude, which is our direction, which means that our direction is 1 over root 3 I plus 1 over root 3 j plus 1 over root 3 k. Now we have the legitimate direction because the direction by definition should be a unit vector. So we now have our direction, we have our speed, and we also have the amount of time that we're traveling, 10 seconds. So the only thing that's missing is the initial position. But it's not really missing. We know what the initial position is. The initial position is 0, 0, 0. So it means that all we have to do here is take our position, okay, our position is considered R of 10. Because if we revisit this equation up here, notice that the only unknown is t. We know what the initial position is. We know what the direction is. T is the unknown. So this here is actually a function of t. So this is the first time that we've seen what we call a vector function, where we could take a t value, plug it in, and find a given vector. Well, the initial vector, the initial position is 0, 0, 0. We refer to that as just zero vector, the zero vector, plus t, which in this case is 10, times the speed, right, which we know is, well, 60. I guess we should reiterate that this isn't really the speed of the helicopter. This is just the magnitude of that vector. And so the speed was given as 60 feet per second. Times the direction, which is 1 over root 3i plus 1 over root 3j plus 1 over root 3k. So we should be able to recognize from this equation where this all came from. This was our R0. This was t. This was our magnitude. This was our direction. And that's what we ended up using in order to calculate that position. So at the end of the day, all we're doing is multiplying 10 times 600, right? Which ends up giving me my quantity that I need for my vector. Which means that my position after 10 seconds is just going to be 600 times each of those quantities. So we're going to be at the position 600 over root 3, 600 over root 3, and 600 over root 3. So if that helicopter keeps going in that exact same direction for 10 seconds, knowing what we already knew, we were able to follow that line and find out where its final position would actually be. Now, the last application we're going to look at involving a line in space is how we could determine the distance between a point that lies off of the line and the line itself. Now, when we refer to the distance, what we mean is the closest distance to the line. And the way we know it's the closest distance is because it would form a right angle. It would form a 90-degree angle. So even though we would say, well, I could go to the line out here, that's not the closest point, and therefore that's not the distance. So we're looking for this distance right here. Now, the only way we can think to possibly do this is to use something that we already know about the line itself. Now, if we're given a line, we're given the initial point, or we're given some point on the line, and we're given the direction that it's moving in. So what we're trying to do is find that distance. So why don't we go ahead and draw a vector from P to S? By doing so, we should realize that we now have a right triangle. And since we know both of those points, we could find what that vector is. So why don't we label that vector as the vector PS? All right, well, if we know that vector and we know the vector v, then we could pick up the vector v right here and put it onto our line. And so if that's vector v, then what we're really looking at here is that there's some angle between the line and the vector that extends to the point that's not on the line. So just to reiterate, what we're trying to do is find the distance called d. Well, let's just think back to what we did with the cross product. notice that if this right here is the hypotenuse of the triangle, then that means that this length right here is nothing more than the magnitude of PS times sine of the angle. Just thinking back to trigonometry, the opposite side over the hypotenuse is equal to sine theta. So multiply both sides by the hypotenuse and we get that D is equal to the magnitude of PS times sine theta. And so we now have a formula technically to find the distance from a point to a line. That formula is that the distance is equal to the magnitude of the vector called PS times sine of the angle between V and PS. Now, that's again kind of a pain, because even though we know how to find an angle between two vectors using the dot product, a lot of times finding that angle is just really complicated to do. It's just a lot of algebra, a lot of trigonometry, right, in order to be able to calculate that. We'd rather maybe come up with some other way to calculate that. And this might seem like a pretty odd thing to do. But what if we were to multiply this here by the magnitude of V over the magnitude of V? I'm not changing it at all because I'm multiplying by 1, but I am making it look a little bit different here, right? And so now if I were to look at this, now I end up getting this distance formula, or this distance rather, of the magnitude of PS times the magnitude of V times sine of theta over the magnitude of V. And I know you're thinking, that just made it more complicated because now I need to know the magnitude of another vector, which I don't know. But don't worry, because this right here, if you remember back from our cross-section chapter, the magnitude of PS times the magnitude of V times sine of theta, that's the area of the parallelogram between PS and V. So it turns out that the numerator is the magnitude of the cross product between the two vectors. And so now, in order to find the distance, we just need to find the magnitude of a couple of vectors and take their ratio. And so why don't we take a look at an example? Here we're given a point that does not lie on the line. And I can show you why I know that this point does not lie on the line. If x is equal to 1, the only time that x could be 1 is if t is equal to 0. But if t is equal to 0 everywhere else, then notice that would imply that I'm at the point 1, 3, 0, not 1, 1, 5. So what that shows us is that S is not going to lie on this line. But what I do know is that line L passes through the point 1, 3, 0. And I could see that that's going to happen when I just plug in t equals 0. That's always going to be the case. And I also see it is parallel to the vector v, which is 1, -1, 2. Those are the coefficients of t. So that's everything that that line actually refers to or tells us. It tells us the initial point, P, and it tells us, or I could even label that P, and it tells us a vector. So now we just have to think about what we need in order to compute what we're asking for. We're saying find the distance from a point to a line. So that means that we need this formula. It's important in multivariable calculus, though, to never just blindly memorize formulas and to actually take the steps to think about what it is that we need to find in that formula. Obviously, we're going to need vector v, which we know. We're going to need vector ps, which we don't know. So let's go ahead and start by finding vector ps. So vector ps is going to be the difference between my 2 points. So remember, it's always s minus p. So we get 1 minus 1 in the I direction. We get 1 minus 3 in the j direction. And we get 5 minus 0 in the k direction. So our vector ps is 0i minus 2j plus 5k. Okay, so at least we know what ps is. ps is going to be that vector, but that's not all I need. I need ps cross v. So now I have to do a little bit more work. I've got to find what ps cross v is by using my determinant. So set up your determinant as I, j, and k. Your first vector is ps, which is 0, negative 2, 5, what we just found. And I'm going to cross that with v, which we knew from the line, 1, negative 1, 2. And now when I work through this process in the I direction, we're taking the magnitude of, the determinant of negative 2, 5, negative 1, and 2, minus, now in the j direction, cancel out that column and we're left with 0, 5, 1, and 2, plus, and now in the k direction, cancel out the k column, and we're left with the determinant of 0, negative 2, 1, and negative 1. All right, well, that must mean that ps cross v is going to be negative 4 minus negative 5, or 1i, minus. Now we cross multiply again, we get 0 minus 5, which is negative 5. So minus negative 5 gives plus 5j. Plus, and now we have 0 minus negative 2, which is plus 2k. So now you should realize that we virtually got most of what we need. We needed ps cross v, we needed vector v, but in order to find the distance between the two, or between the point and the line, we need to take the ratio of their magnitudes. So now we just have to find what is the magnitude of ps cross v and divided by the magnitude of vector v. So this is the square root of 1 squared plus 5 squared plus 2 squared over the square root of 1 squared plus negative 1 squared plus 2 squared. On top, that gives me the square root of 30. On the bottom, that gives me the square root of 6. And if I divide, I end up getting the answer of the square root of 5. So the square root of 5 is the distance between the point and the plane. So just to recap what we went over with lines. Lines can be found in space in 3 dimensions by coming up with a parameterization that describes where I am on the line at different t values. So if we think about t as being time, then that just means you take different times and tell me different points. And when you come up with that parameterization, we can actually come up with a few different applications involving motion, involving like the helicopter problem, where we were able to find out the distance that that helicopter traveled in a certain amount of time. But one really important application is how we can find the distance between a point that's off of the line and the line itself. In the next video, we're going to continue on this idea, except we're not going to be talking about lines. We're going to be talking about equations of planes.